should really be different in like.
Oh, well, I'm tired. Sorry. Cool. Okay, don't worry, I'm not going to read over the entire acknowledgements. That's just legal. But I do want to, it's proof of public release, but I do want to especially express my gratitude to Mr. Ryuji Osawa at Siku Giken for his support and let us know a little bit more about their lithium niobate sensors when we're doing this research. Overview, I'm going to go over the need for why we're looking at electro-optic sensors for radio frequency sensing, and then a quick little overview on the theory behind these sensors, along with the methodology of what we're doing in terms of our use, looking at how do you apply these for outdoor field measurements where you have temperature changes. And that becomes a non-trivial task, and how do you make a temperature calibration. Then going into the methodology results, conclusions, and then followed by questions. As we all know, metal antennas, they can be useful to a degree, but then when it comes to doing large RF measurements in terms of large, talking about electric field measurements, kilovolt meters, and even higher, they can have a few other challenges with them. And specifically, we can start with size. As we know, for metal antennas, say for wideband measurements, you could use something called a D-dot antenna or a displacement dipole type of antenna. And when you're going to say X band or 10 gigahertz, they could be like around, say, this large. You can imagine that's kind of hard to stuff into a small metal cavity. So for instance, you could think of a desktop computer, or let's say inside a vehicle or a car. And what happens is your RF going into these cavities or wherever else, let's say you're just taking them outside, they can bounce from your antenna, bounce around the chamber, go back into your antenna. And therefore you might have other artifacts in your RF measurement that are induced by your antenna, but not actually what you're trying to measure. As we know, it's always for any type of sensor, you're trying to mitigate that as much as you can. And then in addition, bandwidth, depending on the metal antenna technology. For instance, let's say evanescent waveguide antennas. For those antennas are restricted based on the dimensions of the rectangular waveguide. And you can only go to such a low frequency before it doesn't propagate really anymore. But you can use them at higher frequencies. And then in addition, coaxial cables. When you especially go in, say, an outdoor field test setting, you have hundreds of meters, kilometers of this cable. That can become a very challenging problem, especially when it comes to calibration. So for instance, especially as you go to higher frequencies, say again, X band or higher, and you do any wiggling of that cable after you spent hours trying to calibrate them, you're going to have to redo the calibration because they can shift, along with environmental changes that can occur. Now, is there a potential solution? And there is a very promising possibility with electro-optic radio frequency sensors. And they can help address all these issues. Of course, it's not a magic bullet. It does come with a big price tag of only $100,000 usually, versus say a metal antenna could be a couple thousand, $10,000. But there are quite a few advantages, and over time, hopefully the price decreases. So for instance, the small size of these antennas, that's actually the incredible part. So instead of this massive metal antenna, now you can decrease it to about the size of your pinky. And then you can put those into all sorts of other applications. I've seen papers where people have used them for biomedical when trying to do measurements for radio frequencies of certain types of things, but also multi-axial capability. So within these sensors, companies have also been putting sensors in all three orthogonal directions in a very small package. Trying to do that with a metal antenna is basically impossible when you have something about, say, this large, and you have to do that in 3 different ways, or you have to take it 3 different times for your measurement. So time savings is an aspect. Along with the use of fiber optic cable, it gives you a lot more, say, hardness against the environment, and then higher bandwidths. So these antennas, they don't exactly go down to, say, 0 hertz, but they can go anywhere from 100 kilohertz to the low megahertz, and then all the way up to, they're pushing 20 gigahertz and higher. So you can get a nice wide bandwidth when, say, you're doing a ultra wide bandwidth type of measurement as well. So that's a nice advantage. And then finally, high electric field measurements. You might have heard of Captios. They have a electro-optic probe that can survive megavolt meters and even higher types of fields. So different types of electro-optic sensors for different types of needs. And of course, it's the right tool for the job, for which one you use. Now, when I was doing my research for this, I did notice as well, trying to find different types of electro-optic radio frequency sensors, it was a pain, basically. So for instance, if you're doing keywords and you're trying to find them, there's lots of different things, Mach-Zehnder interferometry, and then there's also, for instance, Faraday rotation, different types of sensors, different technologies, but could it be a common term? There is a common term, for instance, when it comes to imaging, for instance, electro-optic, infrared, or IR. But when it comes to this technology, I haven't exactly seen that yet. So I consulted with the National Institute of Standards and Technology, and this was a acronym that we're proposing, and it's simply just EORF, which is fairly easy to remember, and called Electro-Optic Sensors for Radio Frequency Reception. So you don't have to use it, but this is what we're proposing for the community in general going forward when it comes to this class of sensors specifically for sensing radio frequencies. Just make it easier to put all these together in the future as we continue our research. Now, EORF sounds great, but what are the drawbacks, especially when you look at outdoor field test settings? A lot of the different factors for what you'll see in the outside, they can be addressed to a degree. The one that we can't exactly address is the ambient temperature. Even if you have a very strong thermal insulator, let's say you're doing a very long outside test, eventually the outside ambient temperature will get into your probe to some degree, which will affect your measurement. And therefore, that's what we focus on with our paper, is how to calibrate that ambient temperature aspect. And another assumption here, just to point out, is we're looking at nanosecond pulse width type of measurements. Okay. Now, how do EORF probes work? I'll just quickly go over one of them, which is the Mach-Zehnder interferometer, where basically you have a incident optical field that goes into two different legs. They split. One of the legs, say, it has an electrically small antenna or something else going with it that helps to perturb the optical field going through it, and then they recombine, and then there is a constructive deconstructive phasing occurring, and then you would just read it with a photodetector and amplify it, and you can reconstruct your electric field. As long as you have an antenna factor associated with it, you can get an accurate reading. Now, why I bring that up is because within that material that they use, for instance, let's say lithium niobate, you have optical waveguides. And when you have temperature changes, they can physically change in shape of that waveguide. Therefore, that will be changing the magnitude of the optical field going through it. And therefore, you have to calibrate it. Now, there is a good news with this type of technology, is that it has a linear response to temperature. And just to do a quick overview of how they work, there's something called the operating points, and it's sinusoidal. I'm still trying to talk to this. But as you can see, you can go up to what's called the half wave, so V pi, and then under this, you would use the linear region. And that linear region, that just correlates. As long as you're within that, you can get an accurate reading. As you start going towards the limit, then it starts to become nonlinear, and you're going to have error. Now, the other good thing is from the manufacturer, they also did their own, without any applied electric field, a temperature test of their probe. And you can see how there is a linear association between applied temperature and also to the sensor signal. There's some other charges that slowly dissipate over time as well when you reset it back to room temperature. You can explain that later, even after the session. But in general, it's linear, thank goodness. So that sounds great, right? So in terms of the methodology, we put a very tiny gigahertz transverse electromagnetic cell inside an environmental chamber with lots of duct tape and foam and field engineering. But it works. So, and then we use a high voltage pulsar to generate electric field, and we went from there. And the pulse that was sent into the GTEM cell, it's a very fast pulse, therefore it's going to be wideband. And as we know, wideband corrections can be fairly difficult. And that's why I came up with a new type of method of using design of experiments to help calibrate, say, a wideband in this case. Now, before going to the additional details, though, so what happens when you have a RF chamber now inside your environmental chamber? There's going to be other changes. So that's what makes it a little bit more difficult. The gigahertz transversal electromagnetic cell is actually having its own shift on top of this. And that's why we're seeing a parabolic trend occurring with the sensor. So from theory, the manufacturer, it should be linear, but it's not. And unfortunately, for some folks as well, they might just stop here and be like, okay, this is the actual response of lithium niobate. But if you don't consider your RF chamber, then you're going to make that conclusion. But there's something else that goes along with it. So I was trying to look in literature as well, but no one published on it yet, in terms of what happens when you are cooling down and heating up an entire GTEM cell. And we looked at the reflection coefficient, the S11, going into the cell. And what we see here is essentially two main regions. So you have the low frequency where within a GTEM cell, the RF field terminates into, say, a resistor board, or in this case, with this specific design was ferrites, but essentially it works the same way. And then at the high frequency end, it terminates into anechoic foam, which doesn't exactly change with temperature. But the low frequency end, when you have resistors or ferrites, there's usually a linear change with temperature. So that's where you have this additional linear change plus your EO probe, and therefore it creates the parabolic trend. Now, in terms of the calibration aspect, without using a specialized wideband software, in this case, we took the 10 to 90 rise time and then got the frequency off of that, which was 1.46 gigahertz. And then from there, did initial first approximation, taking the low temperature to the control and the high temperature to the control, which was not exactly good enough yet. So that's where the DOE process comes in. Use a split plot design, and the high temperature level, so 15 kilovolts per meter, low temperature, and the high electric field, also 49 degrees Celsius. The low temperature, 1.4 degrees Celsius, and then electric field, 3.3 kilovolt per meter. Did a 2-level test, went through it with 3 repetitions. And then the great thing with design of experiments, and this is what I was using here, is the interaction between factors. In an ideal sense, if the GTEM cell was not having a change, then we shouldn't be seeing the parabolic trend. We should be seeing a linear trend with, I apply an input to the temperature, and then I get an output that's linear. Same with electric field. But if they're coupled, like in this case, then you're going to see a higher contribution percentage for the factors that are combined for temperature and electric field. And then what I did was I slowly shifted, or minimally shifted, the low temperature and the high temperature incrementally until I got the contribution as low as I can. Now, in the an ideal world, everything's perfectly linear. I could probably get this down to 0%, but there's always some type of nonlinearity that could be residual. But the whole point is to lower your error of your calibration, and then any residual would tie into your uncertainty. And then afterwards, this is the calibrated data. Now, we also did a check as well. This is with, there's 2 levels with the control, but just to make sure, we did midpoints using that calibration we just made, and then applied it. And we get an interesting finding, which is pretty exciting, is that, for instance, at the low E field, and keep in mind, electric field biases the operating point. At the low E field, those midpoints are much closer to the calibrated line versus, say, the high electric field. And that makes sense here because what's happening is the operating point is shifting already towards the max of what that electric optic probe can do. And then when you apply additional temperature bias, now you're just pushing it into the nonlinear region. So therefore, additional work that can come from this is you can use this to look at your operating point of your electro-optic probes as well. So that's a potential aspect we can do in the future. And the other aspect about this too is, let's say the manufacturer says this can go up to 20 kV over M or 100 kV over M. You would need to definitely look at the temperature aspect because it may just throw you into a nonlinear regime at a much lower electric field, when you're doing your, say, outdoor temperature measurements. So basically, the right tool for the job, and just understanding the different aspects that can affect your calibrations and also the use of these probes. And so I'm just hoping to be a useful tool and hopefully a useful terminology of the EORF. So thank you so much.